Hello. Today I want to talk about a slightly different topic, which is reinforcement learning. And this is a general machine learning concept that can be applied to a variety of domains. But Hugging Face actually has their own transformer reinforcement learning library, which is something I'm extremely interested to delve into and learn more about. However, before doing so, I wanted to refamiliarize myself with some of the more basic concepts in reinforcement learning. And when I originally tried to do this a few years ago, I audited the University of Alberta reinforcement learning course on Coursera, which is an excellent resource on the topic, and it really goes into detail on this book, which is the Sutton and Barto reinforcement learning book, and this is widely considered to be one of the best texts on the topic. And so I'd highly recommend that course because before taking that course, I had experimented with some introductions to reinforcement learning, and all of them seem to display this diagram, which is an excellent overview on how reinforcement learning works in terms of an agent interacting with an environment with actions, states, and rewards involved. But it doesn't go into high detail on how this could be implemented or how this could be used in real life. And the course really helped me see the applications of this type of machine learning. And so today I'd like to just go through two of the earlier topics in the book and how they could be used to solve very simple problems. And I'm hoping to build on this in future videos to apply it to transformers for text analysis, but also for different types of transformer related problems. And so I think a good first step is to just simply look at the notation used within the reinforcement learning framework. And so as seen in those diagrams, there will be states in the environment, actions that our agent can take, and rewards for taking those actions. But there's also this concept of time, where each step in the process is a discrete time step where the agent can take an action. And as a result of those time steps, we enter new states in the environment. We take actions at those states, and then we find a reward, which, like the current state, is based on the previous action and the previous state within these discrete time steps. And the first concept that's slightly less intuitive is this concept of return, which is notated by G. And so the return, as shown here, is the cumulative discounted reward at a time step. And the return is used because if at a particular time step the reward isn't great, but it leads to greater rewards in the future, we want the agent to learn that. We don't want them to just be deterred from an optimal path because the current reward is poor. And so we use this idea of return to help the agent learn what the optimal path is, even if the rewards along those path at the current time are not high. And so return is a recurring concept that is used in most of the reinforcement learning algorithms. The next major concept, which might be slightly less intuitive, is this idea of policy. Policy can be thought of almost as a probability distribution over the actions that the agent can take. And so our policy defines how our agent behaves. And a lot of these algorithms will be involved with either evaluating a policy to see how good our current policy is, or to optimize a policy. As shown here, the decision-making rule that our agent is using to interact with the environment. And so policy will be another major concept. And the final notation that I think is extremely important is this idea of value. Value can be assigned to a specific state in the environment that the agent is currently in, or it can be assigned to a state-action pair, which is the value of taking the action in that current state. And most of what I'm looking at today is involved with this Q notation, the state action pair value, and optimizing these values can be sort of an indirect way of optimizing your policy, as will be shown with some of the algorithms today. So the first concept that I want to discuss is this idea of multi-armed bandits. This is one of the earliest implementations discussed in the text, and it gets its name from the idea of a one-armed bandit or a slot machine. Except in this context, there are multiple levers that you can pull, and each is assigned a random distribution for the rewards returned for selecting that bandit. And so, in this context, there's not exactly states for our reinforcement learning problem, but there is a value function assigned to each action or each bandit that could be selected. And this value is simply calculated as the rewards associated with taking that action divided by the number of time that action was taken up to the current time step. And so, in order to develop a policy for our agent to use to determine what the best action is to take, we ideally want to just take the action with the highest reward experienced or highest value assigned to the action up to the current time step. But this falls into a common pitfall of not exploring the entire space, where if we select an action early on that gives us a positive reward and therefore has a positive value, we might select that action the rest of the time, even if there is a bandit out there with a higher expected return. And so what we do is we develop this epsilon greedy approach to our policy, where a large percentage of the time we're going to take the action associated with the highest value up to the current time step, but a very small percentage of the time, defined as epsilon, we're going to take a random action to encourage the agent to explore the entire space of actions available. And there's some theory or some schools of thought in terms of defining this probability, this epsilon value, where in the book it notes that between a 10% value for epsilon and a 1% value, the 10% value increases the optimal action choice much more quickly. However, in the long run, the lower epsilon value actually yields the best results, because after the agent learns what the best action is, it takes a random action with a much lower percentage of the time. And the book also notes that you could anneal this value and start with a very high epsilon value and then slowly decrease it over time, so that at the beginning you're exploring the action space much more frequently, but by the end of your training you're not exploring it almost at all. But for simplicity, for my own implementation, I just selected the lower epsilon value of 1%. And so to get into a little bit of the code, first, after importing some standard Python libraries, I created my bandits by assigning a random mean and a random standard deviation to normal distributions, so that each bandit has a normally distributed reward associated with it, and those rewards can be positive or negative. And so to just look at a chart of what this looks like, this is very similar to what was done in the book, where we have several bandits that have negative rewards associated with them all the time. We have some bandits that kind of span the positive negative spectrum, and then we have bandits with positive rewards, and then we have an optimal bandit that has the highest reward associated with it. And so in order to teach our agent to select the best bandit, each time we define our epsilon value at 1%. In the text, step and learning rate are used interchangeably, so this step value is essentially a learning rate. And then in this context, episodes are just the number of selections that we want our agent to use in terms of its learning. And so we define a dictionary of the actions, rewards, and values associated with the actions to track our progress throughout the entire run. We have this function here that gets the value of an action by calculating that average reward associated with the action. And then we have this act function which runs our multi-armed bandit code. And so we can see that at the very top we draw a random number, and if it's less than our epsilon value, we act randomly. Otherwise, we get our values and we choose the maximum, the action associated with the maximum value up to the current time step. Afterwards, we calculate a reward just based on the random distribution associated with the bandit, and then we append this information to our dictionary. And so in order to track the performance of this implementation, I track the average reward over each time step. The time steps being those 100,000 episodes that we defined earlier. And then I printed out some information in terms of the average expected reward if we randomly drew from the bandits, as well as the maximum expected reward if we drew from that optimal bandit every single time. And then I plotted our average rewards to show how this is working. And so if we look at our average bandit, our random draws would bring us to a near zero reward. But if we drew from that maximum bandit every single time, our reward the expected reward, or the mean reward, should be about 9.2, 9.3. And if we look at how our agent performed, we can see that we start very low, and after some sort of deliberation or this learning period, we kind of quickly converge to a slightly below 9.2 value, where we have to keep in mind that although our maximum possible reward, if we chose the best bandit every time, should converge to approximately 925, we're still at 1% of the time throughout this entire process selecting a random action, and that definitely draws down our rewards. And so this is just a quick introduction to the multi-armed bandits and how reinforcement learning is used in a simple context. And in the next segment, I want to talk about Sarsa, which is an algorithm that also uses states to keep track of our state value and state action value pairs. And so the last method I want to discuss in this video is Sarsa. And even though this skips ahead several chapters in the book, I think it's one of the most interesting methods in reinforcement learning prior to getting into very complicated stuff like policy gradients, which I hope to talk about in a future video. But since we skipped past several chapters, I think it's important to note that a lot of reinforcement learning theory comes from the idea of the Bellman equation, or equations of values either for a state or a state action pair, where you assign the value to an expectation of your returns from being in that state or taking the specified action from that state. And so as shown on the screen, these can be computed using our policy, the observed action states, new states, and rewards, as well as this idea of a discount factor or a gamma value. And what the gamma value does is it decreases the impact of previous steps on the estimation of the current value of the state action pair, meaning that more recent actions and more recent states have a higher impact than previous actions and states. And it's a way of trailing off the memory of the agent, so that all the actions and states are still considered, but more recent observations have higher impact. And so moving ahead to the actual Sarsa implementation, here is the algorithm that I'm hoping to show off right now, and this is based on computing the value of state action pairs. We'll then choose an action from our current state using an epsilon greedy policy from the state action values. We'll take that action, observe a reward in a new state, and then we'll recalculate the state action value using the equation shown here, where alpha is our step or our learning rate. We use this idea of the discount factor to apply discounted knowledge and weight more recent actions much more highly. But then we use some of this Bellman mathematics to use the difference of values to sort of compute the value of the previous state action pair. And so having said all of that, I will show the implementation in this notebook. We first assign a discount factor, an epsilon for our epsilon greedy policy, learning rate, and in this case we actually have iterations or steps within each episode, meaning that we're going to run a grid world problem with a maximum number of time steps of 100, and we're going to run that problem 1,000,000 times. And so the idea is that we'll have these functions here where we can take an action by supplying the environment, the action, and the previous state. And what it will do is it'll compute the reward from the square within the grid world, and it'll compute the new state based on the action and the old state, and it'll return the reward and the new state. And so in order to learn our state action values, what we'll do is we'll use this function where we get the dimensionality of the environment. We create a list of possible states, which are essentially coordinates in the environment. We have a list of possible actions, which is stay put. This is move 1 in the x direction, move -1 in the x direction, move 1 in the y direction, -1 in the y direction. And then we assign a value dictionary for each state and each action in that state to capture our state action pair values. And so we can see here we loop over each episode, selecting an initial action and a random initial state, and then we loop over all the time steps in that episode where we get the actions from our current state, and we get the current values of those actions from our current state. And here is our epsilon greedy version of the policy, where having a random draw less than epsilon gives us a random action from this state. Otherwise, we'll take the greedy approach and compute the action that has the highest assigned value currently. And then we do all of our calculations. We assign our new values according to the Sarsa equation, and then we loop through this over and over again with the goal of finally returning a value dictionary for all of the states and actions available. I also created this simulate function that shows off what is happening with the agent across the entire environment, but it does so with a greedy only policy. So after we've used the epsilon greedy approach to compute the best possible policy, or the best possible values for the state action pairs, we simulate the results by having an agent perform within the environment using a greedy only policy, taking out the random actions that were weighing down our bandits from reaching the optimal performance. And so the rest of this is just showing off the examples, which are very interesting. So if we create a random environment where this square within our grid world has a high return and the rest of the squares have a slightly negative return, after learning our values, which I'm not going to relearn since it takes approximately 11 minutes, if we simulate a random starting position, we'll find that using the world wrapping, it gets to the goal in the fastest amount of time, which is very interesting. That one started on the goal, but we can see this red X is our agent's current position, and it loops over the world in the fastest way that it has found, with maybe some flaws based on its learning scheme, but the fastest way that it thinks it can get to our goal. So this is very interesting, but another good question is, what if we add obstacles to this? And so here is another environment created with the idea that these light blue squares are near 0 in value, the dark blue square is our goal, and all of these lighter squares are a barricade of highly negative value squares. And so what happens if we put an agent in this environment and teach it with Sarsa again? Doing so, the learning takes about the same amount of time for a full 1,000,000 episode learning session. But then when we simulate, if we assign a specific starting position like 4, 6, which is outside of the barricade, we'll see that the agent actually learns to use the world wrapping to get to the goal without crossing this barrier of highly negative reward. And I'll just show that one more time with the red X. We're actually wrapping around, avoiding this obstacle completely, and still reaching the goal. And so that was just to show off the power of this algorithm. Sarsa is extremely interesting to me, especially in discrete cases like this, because it uses a fairly straightforward way, but not so straightforward, and it gives us some really interesting results. So that's all I had for this video, and I'm hoping to make more videos on reinforcement learning, but I really appreciate you taking the time to watch, and thank you.